Select the major product of the following reaction. So if we take a look at our reaction, we can look at our starting material and we see that we have a carboxylic acid. And we see that we are reacting that with an alcohol. H+, this generally indicates that we have an acid catalyst. And we are heating this up, so that's an energy source. So we might recognize that these reaction conditions, if we have a carboxylic acid and some kind of alcohol, acid catalyst, and heat, we might recognize that these are the conditions known as Fischer esterification. So it is a way to take a carboxylic acid and make an ester, and the ester that you make depends on the alcohol. So you're going to replace this with OR, and that R group is what's coming from the alcohol that you choose. So if we know that, we might recognize that we're replacing this with this OH with O and that whole side chain. So in this case, so we have that oxygen, and then we just got to get the rest of the chains. We've got that CH2, and then down to this CH with those dimethyls. So that ester should be the product. So if we take a quick look, we can see that here is C. And if we want to, we can take a look at the mechanism as to how that happens, and we can draw that out. So we have our carboxylic acid. And the carboxylic acid is not very reactive. It's electrophilic here at the carbonyl, but not terribly electrophilic. So that's why we have an acid catalyst in there. So the first thing that's going to happen is that you are going to protonate that oxygen of your carboxylic acid. And putting a positive charge on that oxygen is going to make your carbonyl carbon more electrophilic. So this is now a better electrophile, and it can react with even a weak nucleophile like the alcohol that we're trying to add. So at this point, the alcohol can attack that carbonyl carbon, and that breaks the pi bond, giving us this tetrahedral intermediate. So we have a positive charge on the oxygen. So some base that we have in solution, likely going to be just another equivalent of the alcohol, can take that proton. Because we don't want a proton here. What we actually want to do is we want to move it to the OH because we want to set this up to become a good leaving group. So we can deprotonate here. And we're going to get a neutral intermediate. So we have a neutral intermediate. And then if you have a proton source again, so it's an acid catalyst, we've used it here, we regenerated it here, so we can go ahead and use it again. So we're going to protonate that OH. And what that's going to do is set this up to be a good leaving group. Okay, and so this is a better leaving group than just the OH because this would have left us hydroxide ion, a strong base. This is going to leave as a neutral water molecule when these electrons from the oxygen come down to form the double bond and push that off. Okay. Getting us to something that looks very much like the product, just with one extra proton here on the carbonyl oxygen. And in a final step, we can imagine a base in the solution, either the water we kicked off or maybe some more of the alcohol, can go ahead and take this proton. So I'm just going to say base to be generic. So we're, again, reforming an acid catalyst here because we're taking back that H+, and you're getting the ester product.